Okay, good afternoon, everybody. All four of you. I suspect that our job fair is probably wreaking havoc with our class attendance. That and the knowledge that these are recorded and posted. Carson, you must already have a job. You're wearing a hoodie today. Or that you're interviewing with Facebook or something.
Nope, I'm already got a job. I'm good.
All right. Congratulations. I'm glad to hear that.
Thank you.
All right. Let me jump. Whoops, that's not it. Let me jump to some announcements first, and then we'll get back in with our matrix analysis. All right. All right. So I had office hours this morning. Nobody came, which is a good sign. You guys didn't have an assignment anyway pending either, so that probably played a role in that. At least not one that you knew about. Next week, here's my schedule. More or less the same. Office hours Wednesday after lunch, and then again Thursday morning. Excuse me. I just choked down some Chipotle, and I'm not sure it was a great choice right before class. So maybe I should have had crackers or something instead. So yeah, last night watching TV, sat on the couch and posted homework number 3. So that's available to you now. So you guys could take a look at that. It's 8 separate things, but really it's like 3 different problems. There's a truss, the same truss that you worked in homework number 1. And what I'd like you to do is create a SAP model to analyze that truss, and then create a visual analysis model to analyze that truss, maybe the other way around, actually. And then I'd like you to do the analysis of that truss using matrix operations. And so problem number 1 is the SAP model. Problem number 2 is a visual analysis model, or maybe it's the other way around. And then problems 3 through 8 are different steps within the matrix analysis process. And so it's depending on how long it takes you to do the matrix stuff, it will probably take you guys somewhere on the order of, I don't know, maybe a half an hour to do SAP model, half an hour to do visual analysis model. And if I were doing it, the truss analysis would take probably on the order of an hour, starting without a seed file, starting from scratch with a blank Excel sheet. So figure in a little trial and error on your part. You probably got 2 hours for the matrix analysis, maybe a little bit more, and then another hour for the modeling. So that's all. I posted that with it being due a week from tomorrow. So the idea is you would have this weekend to try and take a stab at it. You can ask me questions in class on Tuesday. You can reach out to me in between classes and ask questions too if you like. Then I can answer those questions in class on Tuesday, have office hours Wednesday, have office hours Thursday. You can ask some last minute questions in class next Thursday, and then we can submit that on Friday. So if you guys find that you have some questions about the matrix analysis, then I'm happy to devote some more class time to that. And since this builds off of the truss that we looked at in assignment number 1, I posted the solution to that this morning. Right. And so let me switch gears to our webpage. And so if you go to the homework assignments and solutions, what you should see is there's a PDF now that's available for you to download, and an XLS file that you can download as well for the solution to homework number 1. All right. Also, I took a little bit of time this morning and posted this pre-recorded content and tutorials page. So in here, what you'll find are pre-recorded versions of these first 3 lectures. So if you want to go back and refer to those lectures, you might prefer to watch those. They're a little bit more polished than the in-class versions, but then again, maybe you prefer to just watch the in-class recordings as well. It's basically the same thing, except one is more polished and more formal than the other. And then there's also some tutorials here. We've worked through a couple of these already, and we're going to work through the rest of them. These guys that are highlighted in yellow, those are handouts that I have. I just didn't take the time to post them. I ran out of time for this little project this morning, and so I highlighted him to remind me that I need to come back in and post the handouts. For some reason, when I migrate the class over from last year's Canvas page to this year's Canvas page, the handouts didn't come with it, and I don't understand what I did wrong. So it's easier for me to just upload the handouts again. So, all right, just wanted to make you aware that that's available to you if you want to take a look at that. I don't have pre-recorded versions of analysis 4 and analysis 5, but time permitting, maybe I'll record those and make those available as well. We'll probably come back and deal with those as in-class lectures in a few weeks. My thought is that we would do the truss analysis with matrices, let you guys work through homework number 3, and then we'll shift gears and we'll go back and talk more about SAP modeling again, why you're doing that. So we're kind of going back and forth between 2 or 3 different aspects of the course. All right. So with that, what I wanted to do was to jump in where we left off on Tuesday. And my recollection was that we finished lecture number 2, but we didn't really reinforce that with any examples. So let me open the example problem that we had and take a closer look at that. So as a recap of what we covered on Tuesday, we went through and talked about how to formulate an element stiffness matrix, K sub I, for each of the members in a truss. Then we went and in lecture number 2, we talked about how to assemble the element stiffness matrices into a global structure stiffness matrix, capital K. And then after that, we spent some time talking about how to go about the solution process. And the solution process is pretty straightforward using tools that are available to us in Excel. We can just invert the matrix and then multiply by the loads. But before we invert the matrix, we have to impose the support restraints on the structure. We have to go through one of the 3 different options. One is to delete the rows and the columns in the stiffness matrix, the load matrix, and the displacement matrix that correspond to the restrained degrees of freedom. The second option is to put artificially high stiffness coefficients on the diagonal elements of the stiffness matrix that correspond to the restrained degrees of freedom. And then the third option was to reorder and partition the matrices in order to get to the free stiffness matrix. And then we can go through the matrix operations to get our final solutions. So here we go. All right, so recall that we're looking at this truss here. It has 5 nodes and 7 members. And so for that third process, what we're going to be doing is going through a series of matrix operations where we reorder and partition that matrix. And so this is the series of matrix operations that we go through. We're going to break the stiffness matrix K into the free matrix, the free restrained matrix, the restrained free matrix, and then the restrained strain matrix. Then we can expand that equation there into these 2 equations here. And then we can solve for the displacements at the unrestrained degrees of freedom using this equation. Right. And so what I've done is reordered the elements in the stiffness matrix. So the degrees of freedom 3, 4, 5, 6, 7, 8, and 9 come first, and degrees of freedom 1, 2, and 10 come last. And that's because degrees of freedom 1, 2, and 10 are the restrained degrees of freedom. Now let me shift gears to the Excel sheet. We'll go to Excel solution number 3. And so I have it broken out here. This is the unrestrained stiffness matrix. It has 100 elements in it. It's a 10 by 10 matrix. And then all I've done is here I've just reordered the rows and the columns. And so I'm using references here. And then what I have is I'm breaking this out a little bit. So I have one matrix here that has some lines in it to represent the partitions. And then here I just break it out into 4 different matrices. This step in the solution is probably a little bit extraneous. There's really no need to do this in Excel to get the answer. What I'm ultimately doing is I'm inverting the free matrix. So this matrix down here is, excuse me, the inverse of K sub FF. but I could have easily, I could have just as easily, sorry, I could have just as easily inverted this 7x7 block of cells as well. I just thought it was a little bit cleaner to be able to show you those matrices broken out as opposed to having them in there. And then so we go through and we take the inverse, we multiply the inverse of the matrix by the loads. And so this here, if we do a mouse over, is the matrix multiplication of those two matrices. So we multiply the inverted matrix by the loads and we get the displacements. And again, in here, I could have embedded the two terms, right? I could have taken MMULT parens M inverse of this multiplied by the loads, and I could have saved some space on the sheet, but I just wanted to be clear. And I know you don't have access to this sheet yet, but I'm just kind of walking you through the operations that we used for this. Now, this one is set up like this. So if we had displacements at the supports, we could enter them in here. But I didn't do that. If we had any loads acting on the supported degrees of freedom, we could also add those in here as well. And then down here, what I've got is just the 10 by 1, 10 rows, 1 column matrix of displacements. So this vector here is 7 by 1. It's the displacements at the free degrees of freedom. And then I augment that back to a 10 by 1 that has the displacements at all degrees of freedom. Now, the reason that I do that is that I want to use a reference function, a VLOOKUP function or a match function or an index function to be able to look up the displacements at the degrees of freedom. If we go back to the members tab here, if I want to calculate the end actions for any one of my members, I use a matrix multiplication form where I multiply the stiffness matrix for a given element or a given member by the displacements that correspond to the nodes at the end of that member. And so in this displacement matrix delta, yes, I know, thank you. Then what I do is I use an index option here. And basically that index is a function that allows me to look up a value in another array. So I'm using that index function. Yeah, they changed it. They got the @ symbol in there because there's a new version of the index function. So what that index function is doing is it's referring to that group of cells S50 through S59 down here. So that's oh, that's on a different sheet. Let's go back here. Solution, it's actually referring to solution option number 2. So it's referring to that group of cells and it's giving me the second row, right? So it's saying I want the second row in that index, or I want the first row or the third row, or down here, the 5th row. And so that's what that index function is doing. Then I multiply K times delta, I get the end actions, and then I can use my equations to solve for the member forces. All right, so what you guys should see is a basic step-by-step process at the end of the second analysis lecture. And let me bring that up. So if you go to the last sheet there, then you have this as your step-by-step. These are your instructions for doing problems 3 through 8 on homework number 3. Whoops. Right. So, you know, it's not an easy problem, but it's not something that you guys can't do either. And so I've tried to break it down. I've tried to be anal retentive with the notation so that everything has a unique identifier. I've tried to be specific with the steps so that you guys could make this problem that's fairly challenging into something you guys can do. All right. Questions? Like most of these things, Joe's going to open his mic up.
So it's not uncommon to also look at materials, and like in going through SAP 2000, I noticed like in one of the advanced analysis tabs, like you can specify like S11, S12, S13, which are like the different values within the stiffness matrix, which is similar to how stiffness matrices for individual materials are set up, is there any correlation between like a stiffness matrix for a system versus a stiffness matrix for material? Like,
Okay, so the S11, the S12, those probably weren't stiffness coefficients in SAP. Those are probably stresses that you can get as output.
oh, interesting. Okay.
So you can, if you hack the API, and if you access the application programming interface for SAP, you can actually get it to output the stiffness matrix for a structure for you. Some of you are familiar with Maggie Sullivan Miller, and she's doing a lot of work with comparing the results of different software packages. And that's something that she and I have done when she was trying to debug some of her work. Other than that, I'm not aware of a way where you could access the stiffness matrix directly. So my suspicion is that the S11, S12, those are probably normal stresses that are output parameters for some of the different elements that you can use in SAP 2000. But I'm not positive. There might be something that I'm not thinking of right now, or something that I just don't know about. But when it comes to materials, hang on just a second. Thanks. I should know there's a mute button on my mic here someplace. But anyways, when it comes to materials, at this point, if we're doing a linear first order analysis, the material properties come in the function of a modulus of elasticity, E. And that's the only material property that comes in at all. If we have shear deformations that are included, then we have the shear modulus of elasticity that comes into play sometimes, and that's G. It's not so there isn't a specific stiffness matrix for materials. There's only stiffness matrix for elements or members, and those members are made out of materials, and the material properties are reflected in that value of E or G. If we get into nonlinear materials, recognizing that steel yields, concrete cracks, and things of that nature, then you can input some other parameters into SAP 2000 like the yield stress of the steel. You can put in the tensile strength of the steel. You can put in the strain hardening modulus, E sub T, instead of the elastic modulus, E. But that's well beyond where we're at in class right now, and we're never going to get that far in the matrix stuff. And so there's a whole lot that, in order to implement that in matrix operations, you have to go to an iterative solution process and change the stiffness matrix every time one of the elements changes its stiffness. So it becomes cumbersome. Right. And so what I was going to do is look back here for the element stiffness matrix. I don't know if I have it in this particular slideshow. I guess I don't. So let me see. Let me open another one. No, let's go here. Control open. And I want A01. Oops. Yeah, so this is a slide out of slideshow A01. And really the only reflection of the material is the value of E. And so there's nothing else, there's nowhere else where that material comes into play. Now, in theory, I guess you could have a truss. Let's see, where do I want to go with this? So you could have a truss like this where the members are made out of different types of material. Maybe member A is made out of steel, member B is made out of brass, member C is made out of titanium, member E is aluminum. And in that case, the reflection of the materials would be to have different values of E for each of the different members. All right. Now, still here in lecture A01, when we derived this stiffness matrix, we did it directly in the global coordinate system. So we had a coordinate system here, capital X, capital Y, and we're deriving the 4 rows and the 4 columns of our stiffness matrix by imposing one displacement. So we have 4 degrees of freedom. We have delta X at the first end, delta Y at the first end, delta X at the second end, delta Y at the second end. and we set one of those displacements equal to 1, where the other displacements are set equal to 0. And in so doing, we determine the stiffness coefficients that are in one column of our stiffness matrix. So we go through and we do that on a step-by-step process. And for a truss element, that is not problematic at all. The only deformation that we have is that of a axial elongation or an axial shortening. The only force that we have in the member is an axial force. So working directly in the global coordinate system isn't much of a hindrance at all. But when we get into other types of elements, specifically when we get into frame elements, where the elements have both a rotational stiffness where we can have a bending moment in it, we have a shear stiffness where we have shear forces in it, then working directly in the global coordinate system can be cumbersome. So what I want to do is talk about how we would formulate a truss element stiffness matrix in local coordinates and then convert that stiffness matrix to the global coordinate system. And we don't really need to do this for trusses, but we can illustrate the process using a truss element, and then we can apply the process to beam elements and frame elements later on. And so that's the reason why I'm taking this approach to the explanation. So again, recognize that our ultimate goal is to create a system of equations. K times delta is equal to P, and we want to solve for those displacements delta. Our goal is to develop a set of simultaneous equations that we can solve using the computer. And so we have a member stiffness matrix formulated in the global coordinate system. So I have a capital delta, I have a capital F, and we can develop the member end actions F as a function of K and delta. But here's the stiffness matrix for a truss, right? And then here's the delta and the F matrices as well. Here's a reminder of what the stiffness coefficient is. These stiffness matrices are always symmetric. The diagonal elements are always positive, etc. And for this particular truss, we have 7 members, so we have 7 element stiffness matrices, and we have one global coordinate system, X sub Y. But each one of these elements also has a local coordinate system. So member A has its own coordinate system, lowercase x, lowercase y. Member B has its own coordinate system, lowercase x, lowercase y, etc., etc., etc. So for a system like this with 7 members, we have 8 coordinate systems. We have the one global coordinate system, and then we have a local coordinate system for each of the members. Now, some of the members have a coordinate system that would translate almost directly to the global coordinate system. If you look at members B, F, and D, for example, there's almost no translation required at all because the local x-axis is parallel to the global x-axis and the local y-axis is parallel to the global y-axis. But in those other elements, then some translation is necessary, right? So there's an angle between the local x-axis for member A and the global x-axis, and there's an angle between the local y-axis for member A and the global y-axis. Let me get my stylus for a second. So another thing that's kind of inherent in here is the notion that these members run from the lower node to the higher node. So for member F, for example, this is the ith node here. I don't know why I've got to figure out why it won't be right on the screen. That is so frustrating. Try a different stylus. I've got like 4 of them. No, that's not working either. Huh. This is one reason why I like working from home. I have a different tablet at home that's not associated. This is a Surface that I'm trying to write on now. And the tablet that I have at home is an actual digitizer tablet that's a little bit better behaved. And try and close PowerPoint and open it again. Okay, let's see if I can. Right. So for member F, for example, this would be the ith end here, and this would be the jth end there. But we could go in and define that member the opposite way. Maybe we define it so that's the ith end, and this is the jth end for member F. And so now that member runs in this direction. So that would be the positive local x-axis, and then this would be the positive local y-axis. So the local axis relative to the global axis depends not only on the orientation of the member, but also in how the nodes are defined as well. So if you define the ith node to the right and the jth node to the left, then the angle between the local x-axis and the global x-axis is 180 degrees, and then the angle between the local y-axis and the global y-axis is also 180 degrees. So just something as simple as the definition of the node numbers can change your the mapping between the global and the local coordinate system for a given element. All right, so the goal in this case is to develop a mapping system between two different coordinate systems. And what I'm going to do is I'm going to develop this in terms of a two-dimensional reference frame, just in the XY plane, for example. And then you'll have to take it on faith that it also works in 3 dimensions when we get that far. Excuse me. All right, so we're going to expand our notation a little bit. We have a capital K, capital deltas, and we're going to introduce a lowercase k and lowercase deltas. So capital K is an element stiffness matrix that's written in terms of the global coordinate system, and a lowercase k sub I is an element stiffness matrix that's written in terms of the element local coordinate system. And we have to distinguish between the displacements as well. So if I have a capital delta, then that's displacements that are written in terms of the global coordinate system. Notice it's a delta big X, a delta big Y. And then if I have a lowercase delta here, these are displacements that are written in terms of the local coordinate system, delta little x, delta little y, etc. So the two coordinate systems are shown on this slide here, where we have the displacements in terms of the global coordinate system shown on the left, and we have displacements in terms of the local coordinate system shown on the right. So if we go in and try and develop the element stiffness matrix in the local coordinate system for that truss element, then it would look like this. And so if we impose a unit displacement at the ith end that goes like that, then what happens is we need a force that would be equal to AE over L. So the coefficient that's in the stiffness matrix is no longer a c squared, cosine of phi squared, it's just a 1. And if we look at the force up here that's required in order to hold that in place with a displacement at the ith node, we would need a force up there that is also equal to AE over L, but pointing in the opposite direction. So that means that this element here is a negative 1. Now, if we move, let me erase this. If we move this node up this way 1, unless we account for let me say it this way, if that displacement is relatively small, then there aren't any forces needed to displace that node in that direction at all, right? The member is just going to spin a little bit, and it's not going to create any axial force in the member. So in this case, we have a 0 here, and then the other member forces are zeros as well. And so deriving the element stiffness matrix in local coordinates is usually much more straightforward than developing the element stiffness matrix in global coordinates. What we're going to do now, though, is we're going to develop 2 new matrices, a lowercase gamma and an uppercase gamma, that are used to transform between the 2 matrices. We call it a transformation matrix. We call it a rotation matrix. Those are generally synonymous. The word transformation is probably more general. If we're working in a 2D coordinate system like this one here, then we could call it a rotation matrix, because you could see that each of the 7 local coordinate systems is off by just a rotation, some value of theta or some value of whatever angle you want to use. So we're just rotating the coordinate system. But using the word transformation is probably a more general term and is probably more appropriate. So basically, this is a geometry problem. We want to take the displacements in one of the coordinate systems and map them to the other. So I have a node. That's what this guy is. It's just a joint or a node. And it could displace in the local coordinate system for delta lowercase x, delta lowercase y, or it could displace in the global coordinate system delta uppercase x, delta uppercase y. And so given the angle of the member or the angle between the two coordinate systems, in this case phi, we can use geometry in order to develop a way of converting from one coordinate system to the other. So just using what I'll call simple geometry, it's not always that simple though, we could say that the cosine of that angle phi is equal to delta little x divided by delta big X. So we could say that delta little x is equal to delta big X times the cosine of phi. And if we carry that on for all four of our displacements, we could say that delta little x is equal to, I've got something covering that up. Yeah, is equal to delta y times the sine of phi. We could say that delta y, little y is equal to delta big Y times the cosine of phi. And we could say that delta little y is equal to minus times the delta big X times the sine of phi. Right? So that all works out. That all is well and good. And if we collect like terms here, we could say that delta lowercase x is equal to delta uppercase x times cosine of phi plus delta uppercase y times the sine of phi. And then we could say that delta lowercase y is equal to the opposite of delta uppercase x times sine of phi plus delta uppercase y times the cosine of phi. Now, if you look at these two equations that are down here at the bottom, we can rewrite those equations in matrix form. We can rewrite them like this. And then this matrix of cosines and sines becomes our rotation matrix. And that is a gamma matrix. It's a lowercase gamma matrix because it represents a transformation or a rotation of degrees of freedom at a node. So we're only looking at one node here. Eventually, we're going to deal with the uppercase gamma. And in that case, we're looking at a transformation or a rotation between coordinate systems for both ends of a member at the same time. So we have two nodal displacements or rotations at the same time, and that's an uppercase gamma. All right, now we've developed a way of calculating displacements in the local axes, a local coordinate system as a function of displacements in the global, right? We have delta little x as a function of delta big X and delta big Y. Let's go the opposite way now. Let's develop a relationship between delta big X as a function of delta little x and delta little y. So it's the same approach, except the geometry that I have works a little bit differently. So we have these four relations again. We could say that delta big X is equal to delta little x times cosine of phi. Delta big Y is equal to delta little x times the sine of phi. Delta big Y is equal to delta little y times the cosine of phi. Delta big X is equal to the opposite of delta little y times the sine of phi. So what I'm going to do is collect like terms, right? I have two of these equations that have delta big X, and I have two that have delta big Y. If I collect like terms like that, I can represent that in terms of a matrix, and then I end up with a value of gamma again. So if I go in one direction, if I calculate the local displacements as a function of the global displacements, then I have a gamma matrix. If I go the opposite direction, if I calculate global displacements as a function of local, then I have gamma inverse. All right. All right. Now, so we have some terminology here. We have delta is a vector of displacements in the global coordinate system. We have little delta is a vector of displacements in the local coordinate system. And then we have a transformation matrix. And so what we have is a gamma on the left and gamma inverse on the right. And if you look at that, I think everybody would recognize that the inverse of gamma is actually the transpose of gamma. And that is true because gamma is an orthogonal matrix. Now, again, the amount of stuff that I remember from my linear algebra would fit inside my Chipotle cup, and there'd be a lot of room left in there. So I don't necessarily need you to remember this, but it's a property that helps us because when we determine what this gamma matrix is, we don't necessarily need to go through the formal inversion process, which takes time and takes computational resources. We can just transpose the matrix instead, and that's much more efficient. All right, so that's the process of calculating or deriving a lowercase gamma matrix, and that's the converting displacements at one point. What we want to do now is we want to convert the displacements for an entire member, which means converting 4 degrees of freedom instead of just 2 degrees of freedom. So basically what we're going to do is we're going to go at this like this, where we have a delta sub k equal to gamma times delta sub k, where lowercase delta is a 4x1 element displacement matrix in the local coordinate system. Capital gamma is a 4x4 rotation matrix or transformation matrix for the member that we're looking at. And then we have a big delta k, which is the displacements in the global coordinate system. I have that little blue line there. Sometimes I use those to line things up on my slide, and I probably forgot to delete that. So what I can do is I can rewrite that, and I can rewrite that in these terms here. So I have this matrix, which is really another matrix. That's delta x1 and delta y1. And then this here is delta x2 and delta y2. So those are capital X's, capital Y's for the first node and for the second node. And then over here, this guy is delta lowercase x at 1. This is delta lowercase y at 1. This is delta lowercase x at the second node, and this is delta lowercase y at the second node, right? And so we can expand those like that, and now we have these displacements that are each 2x1. So the capital gamma matrix is basically just a augmentation of the lowercase gamma matrix, recognizing that we're really just transforming 2 nodes at the same time. And so what you find here is that there's really no mapping that occurs between the degrees of freedom at the first end and the degrees of freedom at the second end. So that's why we have a block of zeros here and a 0 here, because they're completely decoupled. If we move one of the degrees of freedom at the first end, it doesn't affect the degrees of freedom at the second end, and vice versa. All right, so in this case, we have delta little x and delta little y, which are scalar values in local coordinates. We have delta big X and delta big Y, which are scalar values in global coordinates, right? And so for the whole structure, we can write this k delta equals times p. And so we can rewrite that in global coordinates, and we can rewrite that in local coordinates for each of the elements. And so we can go through a process of substitution, where we can write that the end actions are equal to the rotation matrix times the end actions, except in this case, we have the end actions in local coordinates, and here are the end actions in global coordinates. Here are the end displacements for the degrees of freedom in local coordinates. These are the end displacements in global coordinates. So we can go through and do some manipulation, and what we can find is that we can develop the global stiffness matrix by going through a series of matrix operations where we take gamma transpose times the stiffness matrix in local coordinates times gamma. And then we can expand that, and we can do that for each of the element stiffness matrices. So if we derive our stiffness matrix in local coordinates, we can convert it to a stiffness matrix in global coordinates. And this process involves pre-multiplying by the transpose of gamma and then post-multiplying by gamma itself. And so when you read textbooks or you talk to different experts on this, then this process is typically referred to as pre and post multiplication, because you take the value of lowercase k and multiply it by the transpose of gamma, and then you multiply by the original value of gamma. All right, now, so now that's going to be on every slide. Why is that on every slide? This computer has just got something quirky with it. Maybe I should just wipe it and reinstall everything. I don't know. So if we consider a truss element where we have a stiffness matrix in local coordinates, what we can do is develop the stiffness matrix in global coordinates by pre and post multiplying. So I have my rotation matrix, and I've gone back to the compact notation where C is equal to the cosine of phi, where S is equal to the sine of phi, etc. And if you go through that series of matrix operations, then ultimately what you'll end up with is the original stiffness matrix that we derived in the global coordinate system. All right, I hit escape and that thing went away. I like to think that I know how to use PowerPoint, but for some reason that's just baffling me. All right, now for truss elements, it makes little difference whether we derive them in the global or the local coordinates, but for frame elements, it's very cumbersome to derive the element stiffness matrix directly in global coordinate systems. So when we get to frame elements, we all have almost no option but to use pre and post multiplication for the process. And so when we evaluate this in member forces in our local coordinates, we can go back to the local formulation. So we have lowercase f here. No, I won't write it all. I don't know what I'm doing wrong. I really don't. Yeah. Right. So all right, I just can't use a pen. So on the right there, you have a lowercase f, which is the end actions in local coordinates. And so those are aligned along the length of the member. So rather than having to solve for the member force using geometry at the end, we could just determine the member force by taking it equal to f sub lowercase x2, or we could take it equal to the opposite of f sub lowercase x1. And that saves some time on the back end as well in determining what those forces are. So here's our process again. This is the step-by-step process for doing an analysis of a truss using the direct stiffness method, developing the stiffness matrices in global coordinates. And so step number 2 here relies on the idea that we have all of our element stiffness matrices already in the global coordinate system. But if we do this in a slightly different approach where we develop the stiffness matrices in local coordinates, then we have to go through a pre and post multiplication step in step 2 in order to get the stiffness matrices in terms of the global coordinate system. So this doesn't have any bearing on homework number 3. In homework number 3, I'm asking you to go through the process using the formulation in global coordinate systems. But when we get into a subsequent homework, we'll ask you to go back through and rework the problem using the pre and post multiplication approach. All right, now I'm going to call it good for today at that point. So what you guys have some work to do. You could go in and start creating your visual analysis in your SAP 2000 model for the truss, and then you could start developing a spreadsheet with the matrix operations that you're going to need in order to solve for those member forces. Now, so the idea is that you should get the same member forces and approximately the same nodal displacements out of visual analysis, out of SAP, and out of your matrix solution. So asking you to do all 3 in the same assignment isn't necessarily me being sadistic, but it's not necessarily me not being sadistic either. But it gives you a means of checking your work. And I think even in the page that gives you the assignment, I gave you a couple of the stiffness coefficients from your global stiffness matrix, so you could spot check your global stiffness matrix to see if you're on par with my solution for the problem. All right, so in general, a little bit of pain is good. So if this hurts a little bit, then chalk that up to the learning process. If it sucks a lot, if it hurts a lot, then just stop and then reach out to me, and we can either talk one-on-one, or you could reach out to me at the beginning of the next class, and maybe some of your peers would also benefit from your agony. So yeah, my goal isn't necessarily for you guys to spend hours and hours and hours working on this. And I know sometimes trying to find a mistake in a series of operations like this it can be problematic. It can be tough, difficult to find mistakes in this. So if you get to a point where you've spent a couple hours on the matrix stuff and you're either stuck and you don't know what to do next, or maybe you've gotten through it, but your answers just don't match, just send me your spreadsheet, and odds are I could probably find the mistake in 10 or 15 minutes and then get you going back on the right path. All right. I think, like I said at the beginning of the semester, this part of the class, the matrix operations, is probably the least potable part of it for some of you. It's the part you're going to like the least. Others, you're going to enjoy this like I do. But I think that this adds a good context to the rest of the work that we do in SAP and visual analysis. So, all right. So with that, I'll hang around for a few minutes for questions, but otherwise, you guys can hit me up over the weekend, or I'll see you again in class on Tuesday. All right. So with that, I'll go ahead and end class and bid you a happy weekend.